Somewhere above your head right now, about 36,000 kilometers up, there is a graveyard shift going on. Hundreds of satellites, still working, still useful, and slowly running out of fuel.
And as of last night, there is finally a mechanic on the way.
Good evening, and welcome to Astronomy Daily. I'm Anna.
And I'm Avery. Coming up, a spacecraft with arms launches on a mission to keep other spacecraft alive. A rocket stage is 2 weeks out from hitting the moon, and astronomers have just put out a call to arms about it.
We've got two stars that were born together, lived together, and then died in sequence, leaving behind the first pair of supernova remnants ever traced back to a single binary.
The first complete magnetic map of a galaxy cluster, an asteroid breakup that may have bombarded 3 worlds and helped freeze our own.
And a skywatching window that is closing faster than you'd like.
Let's get into it.
So, Avery, here's a problem that has quietly bothered the satellite industry for about 60 years. You build a satellite, you spend hundreds of millions of dollars on it, you put it in geostationary orbit, 35,786 kilometers up, where it hovers over the same patch of ground forever. And it works beautifully for 15 years. And then it runs out of fuel.
And that's it. The hardware is fine.
The hardware is often perfectly fine. The cameras work, the transponders work, the solar panels work. But without propellant, it can't hold its position, so it drifts and it becomes junk. You throw away a working satellite because the tank is empty.
That is a spectacularly wasteful way to run an industry.
It is. And last night, Northrop Grumman launched the most serious attempt yet to fix it. At 5:15 in the evening Eastern Time on Tuesday, the 21st of July, the Falcon 9 lifted off from Space Launch Complex 40 at Cape Canaveral, carrying the mission robotic vehicle, plus 3 mission extension pods.
Mission robotic vehicle. What does it actually look like?
Picture a satellite bus with 2 arms, 2 robotic arms, each about 3 meters long, 10 feet, built by the United States Naval Research Laboratory and supplied through DARPA's Robotic Servicing of Geostationary Satellite program.
So this is a genuinely dexterous machine, not just the tug that bolts on.
That's the distinction that matters. The MRV can inspect, it can relocate, it can repair, it can upgrade. And its headline job on this mission is to pick up those 3 mission extension pods and install them on client satellites that are running low on propellant.
So the pods are the actual fuel solution.
Think of them as jetpacks. Each pod clamps onto a satellite and takes over orbit control and momentum management using electric propulsion. Each one can handle a satellite of about 2,000 kilograms. That's a typical big geostationary bird, and give it up to 8 more years of life.
8 years on a satellite that was otherwise finished?
8 years. And the MRV itself carries something called a passive refueling interface, which is the first refueling interface approved by the U.S. Space Force. So the servicer is itself designed to be refueled later.
Now, Northrop have done a version of this before, haven't they?
They have, and this is why they're the ones doing it. Mission Extension Vehicle 1 launched in October 2019, the first commercial satellite servicing spacecraft ever, and 4 months later it docked with communication satellite Intelsat 901 in geostationary orbit. MEV-2 followed in August 2020.
So what's different this time?
Those earlier vehicles were one-to-one. One servicer went to one satellite, docked with it, and stayed there doing the work itself. The MRV is one-to-many. It carries pods, installs them, and moves on. It's the difference between a tow truck that has to stay attached to your car forever and a mechanic who fits a new part and drives off to the next job.
That scales.
That scales. And there's a nice detail on the launch itself. The Falcon 9 booster, B-1069, was flying its 32nd mission, and it was deliberately expended, no landing.
Why give up a booster with 31 flights on it?
Because geostationary transfer orbit is demanding, getting that much mass that high needed every bit of performance the rocket had. And there wasn't propellant left for a landing burn. SpaceX made the trade.
So when does the actual servicing start?
Not for a while. The MRV and the 3 pods each separate and then climb to geostationary orbit under their own solar electric propulsion. And that climb takes up to a year. Servicing operations are expected to begin in 2027. After the initial checkouts, the RSGS program gets handed over to the U.S. Space Force.
A year of just going up.
Slowly and efficiently. Electric propulsion is patient. And at the end of it, for the first time, there's a repair capability parked permanently in the most valuable orbital real estate we have.
Right, from a machine built to preserve spacecraft to a spacecraft that is about to be very thoroughly destroyed.
This is one we've been tracking.
It is, and I want to be upfront about that. We covered this back in June in episode 125. But there is a genuine reason to come back to it, because the science community has just done something about it. The short version, for anyone joining us since, in January 2025, a Falcon 9 launched 2 commercial lunar landers, Firefly's Blue Ghost and iSpace's Hakuto R Mission 2. It did its job, but the upper stage, cataloged as 2025-010D, never came home. Instead of burning up in our atmosphere, it ended up in a long looping orbit through the Earth-Moon system. And somebody noticed.
The independent astronomer Bill Gray, who runs Project Pluto and tracks this sort of high-orbit debris, his software flagged an impact. On the 5th of August this year, that stage hits the moon.
So what's new? 3 things. First, a new preprint has just gone up on Archive, and it is signed by 23 astronomers. It is essentially a call to arms. They're asking the scientific community, professional and amateur, to point everything they've got at the moon on the 5th of August.
Because this is a rare thing.
Because we almost never get this. We get natural impacts on the moon all the time, but we don't know when they're coming. Here, we know the object, we know its mass, we know its structure, we know its velocity, and we know the time to within about a second. That is an artificial impact experiment we didn't have to pay to set up.
And the timing has been tightened, hasn't it?
That's the second new thing. Gray's latest published calculation, dated the 17th of July, puts the impact at 6:34 and 32 seconds UTC. Earlier coverage back in May was quoting 6:44. So if you've got the old number written down, update it.
And the third.
The third is the actual physics prediction, and this is the part I find genuinely interesting. The paper models what happens on contact. This thing is roughly 12 meters long and about 4,000 kilograms, and crucially, it's hollow. It's a tank. So the prediction is that it crushes rather than punching deep.
Like a can rather than a bullet.
Exactly like a can. And the result of that is a relatively shallow crater. They're estimating 20 to 30 meters across, but a very large ejecta plume. Kilometers of debris thrown up off the surface.
So the plume might be the visible part.
That's the hope, and it's a subtle bit of reasoning. The impact site is near the crater Einstein, right on the moon's western limb, about the 10 o'clock position on the disk as you look at it. Now, that's awkward because it's on the sunlit part of the surface. And no impact flash, artificial or natural, has ever been recorded on the lit face of the moon. The glare defeats you.
But being on the limb helps?
Being on the limb might save it, because rocks thrown up from a site that close to the edge rise off the moon entirely. And once they're off the limb, they're silhouetted against black sky, catching sunlight. So you might not see the flash, but you might see the plume.
Who else is watching?
NASA's Lunar Reconnaissance Orbiter will image the site before and after, which gives a clean comparison. And South Korea's Pathfinder Lunar Orbiter is going to attempt to observe as well. There's precedent for the after image too. When a Chinese rocket stage hit the far side in 2022, LRO found the site, and it had made not 1 crater, but 2.
And there's a longer-term payoff to all this.
And this is why the paper matters beyond the spectacle. They want to test a method for pinpointing exactly where an object strikes the moon using the observations. If you can nail that down against a known impact, you validated a technique, and that feeds directly into planning seismic experiments on the lunar surface for future missions.
Now, the practical question, who actually gets to see this?
And this is where our North American listeners want to pay attention, because this one is squarely yours. 6:34 UTC on the 5th of August is 29 minutes past 2 in the morning Eastern Time, 1:34 Central, 12:34 Mountain, and on the West Coast it's still the night before, 11:34 in the evening on the 4th.
Middle of the night, but the moon is well up.
The moon is well placed across the continent, and the paper specifically identifies observers in the Americas as the ideal group. If you have a telescope and you've ever wanted to contribute to something real, this is the night. They are explicitly asking amateurs to take part.
And for those of us further around the globe,
Less kind, and I'll be straight about it. For us in Australia, that's 4:34 in the afternoon, broad daylight. New Zealand, early evening, no good either. The UK and Europe get 7:30 in the morning, which is also daylight. So the live event belongs to the Americas.
but the aftermath belongs to everyone.
The aftermath belongs to everyone. The LRO before and after imagery, the crater measurements, the analysis of how well the predictions held up. And frankly, the question sitting underneath all of this is global. We are about to start putting people back on the moon, and we are currently hitting it with our own rubbish, by accident, without warning.
All right, Avery, moving on to our next story. More than half of all stars are in multiple systems, 2 or more suns orbiting each other. And for the really massive stars, the ones destined to explode, that fraction is even higher.
So most supernovas should have had a sibling.
That is exactly the implication. And yet, until this week, astronomers had never found a single case where both stars in a binary exploded and both left behind remnants we can still see.
Not one out of how many?
We've cataloged around 300 supernova remnants in our galaxy, not one confirmed sibling pair. And the reason is a bit embarrassing, actually. One of them was probably sitting in plain sight the whole time.
Go on.
The Jellyfish Nebula, IC 443, in the constellation Gemini, about 6,000 light-years away. It is one of the best-studied supernova remnants in the sky, and one of the brightest gamma-ray sources of its kind. If you could see it with your eye, it would look bigger than the full moon.
And something was hiding behind it.
Next to it, there's a much fainter object called G189.6 plus 3. It was first picked up in 1994 by the German Rosat satellite as a faint X-ray glow, and later the Russian-German Spectrum Röntgen Gamma Observatory saw shell-like structures in it, which suggested it was also a supernova remnant. But it sits right up against the glare of the jellyfish, and that glare drowns it.
So how did they finally separate them?
16 years of data from NASA's Fermi Gamma Ray Space Telescope. The team, led by Miltiades Michaelides, a postdoctoral fellow at Stanford, essentially subtracted the jellyfish out, isolated its gamma ray emission, and looked at what was left underneath.
And there was something left.
There was. G189.6 plus 3 is independently producing gamma rays, which matters enormously because gamma rays mean particle acceleration, and particle acceleration is what a supernova remnant does. It's the shock wave doing work.
Michaelides had a nice way of putting that, didn't he?
He compared it to a drop of water falling on a still lake. The ripples spread out from the point of contact. A supernova remnant does exactly the same thing. And if you can see the ripples, you know something dropped.
So we have two remnants next to each other. How do we know they're related rather than just an accident of line of sight?
This is the elegant part. There's a filament of gas arcing between them, and that filament is where the shock wave from G189.6 plus 3 has slammed into the same molecular cloud that the jellyfish is pushing against.
Same cloud, so same distance.
Same cloud, same distance, same neighborhood. They're not one in front of the other. They're genuinely next door to each other. And that's what makes the shared origin story credible.
So walk me through the story they're proposing.
A tale of two massive stars, born together, gravitationally bound, orbiting extremely closely, perhaps only a few times the Earth-Sun distance apart. Close enough that material was likely flowing from one to the other, and then the bigger one runs out of fuel and detonates.
And the explosion breaks the partnership.
The explosion breaks the partnership. The binary is disrupted, and the surviving companion is essentially kicked, flung off through the galaxy on its own. It keeps traveling, and tens of thousands of years later, it explodes too.
How far apart did they end up?
The centers of the two explosions are now somewhere between 30 and 50 light years apart. Two stars that were once close enough to be exchanging material, now separated by that gap, and each marked by its own expanding shell.
What were they?
The jellyfish's progenitor is thought to have been something like 15 to 25 times the mass of the Sun. Its companion at least 20. Both were probably tens of thousands times more luminous than the Sun, and both may now be neutron stars.
And publication status? Because I know this was previewed at a conference.
Good flag. Miltiades presented the results at the American Astronomical Society meeting in Pasadena back in June. What's happened this week is the peer-reviewed paper. It's in Nature Communications, with the Stanford release and wider coverage landing on the 21st.
And one for our listeners, can we go and look at any of this?
Not this month, wherever you are. Gemini is close to the Sun at the moment, so it's lost in the glare globally. But it comes back, and this is one where Northern Hemisphere listeners get the better deal. From North America and Europe, Gemini rides high overhead through winter, December into March, and the jellyfish sits beautifully placed for a telescope or a long exposure.
And from down here?
We still get it, just lower. From Australia and New Zealand, Gemini comes up in the northern sky through our summer. Visible, worth hunting, but closer to the horizon. Either way, put it on the list for the end of the year. And bear in mind the jellyfish is faint. It would be bigger than the full moon if your eye could pick it up, but it needs photography or a decent aperture to show itself.
Anna, here's something we know exists but have never actually been able to draw. Galaxy clusters, the largest gravitationally bound structures in the universe, hundreds or thousands of galaxies plus enormous clouds of hot gas plus dark matter, are threaded through with magnetic fields.
We've known that for decades.
What we have never done is map the shape of one across an entire cluster, from the middle right out to the edge.
And now somebody has.
A team led by Andrea Botton at INAF, Italy's National Astrophysics Institute, has reconstructed the magnetic field of galaxy cluster Abell 2255. And I want to be precise about that name because at least one outlet has got it wrong this week and called it Abell 2142. It is Abell 2255, about 1 billion light years away.
Why that cluster?
Because it's famously messy in radio. Abell 2255 has long been known for its complexity. It's full of strange, diffuse radio structures, halos, and filaments, which is exactly what you want if you're trying to trace magnetic fields, because those structures are made by energetic electrons spiraling along magnetic lines.
So the radio emission is the field, effectively made visible.
It's the tracer. Electrons corkscrewing along magnetic lines give off radio waves. So if you can see the emission finely enough, you can work backwards to the field. The problem has always been that these signals are extraordinarily faint.
What did they observe with?
LOFAR, the low-frequency array, the European radio telescope, spread across a continent. And these are the deepest radio observations ever made of a galaxy cluster. That was combined with a new data analysis technique, and between them, that's what cracked it.
And what does the map show?
This is the finding. In some regions of the cluster, the magnetic field lines are strikingly coherent. They follow very specific directions, stretching radially outward along the extended radial structures. They're not random.
Which tells you something made them that way.
Which tells you something is organizing them. And Botton's conclusion is that the shape of the field is intimately linked to the motion of the gas it sits in. The field gets stretched and compressed by the movements associated with the cluster's own formation.
So the cluster assembling itself is what shapes the magnetism.
That's the argument, and it's the first observational evidence of it. The same violent process that builds a galaxy cluster Gas falling in, sloshing, colliding, merging is the process that combs the magnetic field into the pattern we now see.
And that ties into the radio halos question.
It does. Bolton says they believe the mechanism that switches on these gigantic radio emissions is linked to the formation process of the clusters themselves. So the map isn't just a pretty picture, it's the evidence for the engine.
It's a lovely example of the thing radio astronomy does best.
Showing you a structure that is completely invisible, is a billion light years away, is bigger than anything else in the universe, and has been sitting there the entire time. Published in Astronomy and Astrophysics.
Avery, if you want to know what has hit the Earth, don't look at the Earth.
Because the Earth keeps erasing it.
Constantly. Plate tectonics, volcanism, weather, water, erosion. Craters get buried, distorted, subducted, destroyed. The practical consequence is that geological evidence for impacts older than about 650 million years is extremely scarce here.
And the moon doesn't do any of that.
No plate tectonics, no flowing water, no meaningful atmosphere. The moon just keeps the receipts. And when you read those receipts carefully, there's a spike.
When?
Around 800 million years ago, there's a surge in large lunar impacts, and it shows up in two independent ways. One is the estimated ages of big craters, including Copernicus, which is 93 kilometers across. The other is impact glass.
Explain impact glass.
When something hits hard enough, the heat melts rock. That melt cools into glass, and the glass locks in a chemical timestamp. The Apollo missions brought a lot of it home. And when you look at the age distribution of that glass, you see the same spike at 800 million years.
So, two different methods agree that something happened, but nobody knew what.
Nobody knew what. That's the puzzle that's been sitting there for decades. And a new paper led by Dr. William Bakke at the Southwest Research Institute in Boulder proposes a specific culprit.
Which is?
An asteroid called Eulalia, or rather the parent body of the family of asteroids we now call Eulalia, because the object itself no longer exists. It was catastrophically broken apart in a collision in the main belt.
And the location of that breakup matters.
The location is everything. It happened right next to what's called the J3-1 resonance with Jupiter, and a resonance like that is essentially a gravitational trapdoor. Material that wanders into it gets its orbit pumped up by Jupiter and flung into the inner solar system.
So the shrapnel had a delivery mechanism waiting right there.
It had an open door right next to it, and the simulations show what happened in two phases. Half the fragments reached the resonance almost immediately. That's the prompt bombardment, planetary shrapnel sprayed across the inner solar system.
And the other half?
Over the following 100 to 150 million years, another quarter of the fragments drifted into the resonance more slowly, pushed by something called the Yarkovsky effect.
Which is what in plain terms?
It's sunlight doing work. A rotating asteroid absorbs sunlight on one side and re-radiates that heat as it turns. That re-radiation gives an incredibly gentle push. On a human scale, it's nothing. Over 100 million years, it can move an asteroid's orbit enough to drop it into a trapdoor.
So this wasn't one bad afternoon. This was a long siege.
That's the reframing I think is genuinely important here. Not an event, an episode. A bombardment that opened suddenly and then kept going for well over 100 million years.
And what does that mean for Earth?
Here's the number that changes the scale of it. For every large impact recorded on the moon, roughly 20 similar or larger impacts hit the Earth, where a bigger target with stronger gravity.
20 to 1.
20 to 1. So a spike on the moon means a barrage down here. And now look at what else was happening around 800 million years ago. That is the run-up to one of the most dramatic climate episodes in our planet's history. Widespread global cooling and major shifts in the biosphere.
Is he claiming a causal link?
He's careful, and I want to be careful too. Bakke's phrasing is that given the peak of this barrage coincides with a period of widespread cooling and major shifts in our biosphere, it is tempting to suggest the former produced the latter. That is a hypothesis flagged as tempting, not a conclusion.
Because so far only one impact has ever been firmly tied to a biological outcome.
Chicxulub, 66 million years ago, the end of the dinosaurs. That's the one. Everything else is inference.
So how would you ever test this?
This is my favorite part of the paper, and it's the reason to keep an eye on this story. We have asteroid samples on Earth right now. Hayabusa 2 brought material back from Ryugu in December 2020. OSIRIS-REx brought Bennu back in September 2023. Both are under analysis.
And if they carry the Eulalia fingerprint?
If the mineralogy matches the Eulalia family, then we are holding, in a laboratory, physical samples of the material that reigned on the inner solar system 800 million years ago. That would turn a dynamical model into a direct compositional record.
That's a remarkable thought. Brains in a lab in Japan and Texas that might be pieces of the thing that helped freeze the Earth.
Published in the Planetary Science Journal by Botke with Vokrolitsky, Dijkhuis, and Zellner.
Right. And our next story comes with a deadline wherever in the world you're listening.
What's the urgency?
The moon. First quarter was yesterday, the 21st. Tonight, it's a waxing gibbous, and every night from here, it gets brighter and stays up longer, building to the buck moon, full at 4:36 in the afternoon UTC on Wednesday the 29th. That's 10:36 in the morning Eastern Time in the States and 12:36 on Thursday morning for us in Australia.
And that matters because of what's peaking.
The southern Delta Aquariids. Peak falls on the 30th, effectively the same night as the full moon. So the peak is going to be washed out, which means the practical advice is the same for everybody. Don't wait for peak night. This week is your window, in the small hours while the moon still sets and leaves you real darkness before dawn.
And this is a shower that favors us.
It does. From Australia, New Zealand, and southern Africa, the radiance sits high, close to overhead, which is why the shower gets underrated in the north. Under genuinely dark skies, you might see 15 to 20 an hour, and they're lovely meteors. Long, graceful streaks rather than quick flashes, and known for persistent trains, those glowing trails that hang in the air for a second or two afterwards.
And northern listeners aren't shut out of this one.
Not at all, and I want to be clear about that, because this shower gets written off in the north too readily. If you're in North America, particularly the southern states, Texas, Florida, Arizona, the Gulf Coast, the Delta Aquariids are a genuinely worthwhile watch. The radiance sits low in your southern sky rather than overhead, so you'll see fewer of them, but the ones you do catch travel long paths across the sky, and they can be spectacular. Best time is after midnight through to dawn. Southern Europe, the Mediterranean, North Africa, same deal.
And where do people look?
The radiant is in Aquarius, near the star Delta Aquarii. Use Fomalhaut to find the region. But honestly, don't stare at the radiant. Lie back, take in as much sky as you can, and let them come to you. Parent body is suspected to be comet 96P Machholz. There are also the Alpha Capricornids building to the 30th and 31st. Far fewer meteors, but famous for slow, brilliant fireballs that can punch straight through moonlight.
And for the north, there's something considerably bigger coming.
There is, and if you're listening in North America or Europe, you should be planning for this now. Two things land together on the 12th of August. First, the Perseids peak, and this year the moon is new that same day, which means a properly dark sky. That is the best Perseid year in some time.
And the second?
A total solar eclipse. The first on mainland Europe since 1999 and the first in Spain since 1905. Totality sweeps across the Arctic, Greenland, Iceland, and northern Spain. And in Spain, it happens close to sunset with the sun only a few degrees above the horizon, which could be extraordinary.
North America doesn't get totality this time.
No, and I won't oversell it, but there is a real partial eclipse across much of the continent. Alaska gets the deepest view near sunrise. Atlantic Canada gets roughly half the sun covered at maximum in the afternoon. New England and the northeastern states get a smaller bite, and there's some coverage visible right across every Canadian province and the northern contiguous states.
So dig out the glasses.
Dig out the eclipse glasses from 2024 and check their ISO 12312-2 certified. It will not get dark. Even with 50% coverage, the remaining sun is blindingly bright, so there is never a safe moment to look without protection. And a lovely detail, if you're standing in the path of totality in Spain or Iceland, there's a genuine chance of a Perseid streaking past during those 2 minutes.
And tonight, for everyone,
The Milky Way. From the southern hemisphere, the galactic core is riding high overhead right now. One of the real privileges of our winter, and it's at its best. From the northern hemisphere, it's lower, in the south towards Sagittarius, but on a dark night, it's still magnificent. And before dawn, Saturn and Mars are in the eastern sky for both hemispheres.
one more thing before we go.
The launch watchers. SpaceX is targeting Thursday the 23rd for Starship Flight 13. Window opening at 6:45 in the evening Eastern Time. That's 5:45 Central, 3:45 Pacific, and Friday morning, 8:45 for us in Australia. 20 Starlink V3 satellites aboard. Second flight of the V3 vehicle.
Dead an alarm.
And as always with Starship, check before you commit. The date has already moved twice.
That's Astronomy Daily for Wednesday, the 22nd of July. A mechanic on its way to geostationary orbit. A rocket, stage 2, 2 weeks from making a new crater. And 23 astronomers asking the world to watch.
2 stars that died in sequence and left their remnants side by side. The first magnetic map of a galaxy cluster. And an asteroid breakup that may have been raining down on us while the Earth froze.
Show notes, sources, and links are all at astronomydaily.io, and you can find us at Astro Daily Pod across the socials.
If you enjoy the show, a rating or review genuinely helps other people find us. Astronomy Daily is part of the Bytes.com podcast network.
I'm Anna.
And I'm Avery. Get outside this week. It won't be dark for long.
Clear skies.
Astronomy.